Hello everyone and welcome back to lecture 19 of Spatial Statistics and Spatial Econometrics. In this lecture, we will build on the knowledge that we have accumulated till now with regards to the spatial regression models. So at first, we studied the impact of uh, spatial dependence in model error. What does that mean? That means if I were to think about a regression model, y equals x beta plus u, which is a multivariate regression model where y is my outcome variable, x are my regressors, and beta are the model parameters, and u is the error term, something that I could not explain in this model. These things we have seen quite many times in the past. Then if there is spatial dependence in model error, where does spatial dependence come from? We have discussed that what we really mean by that is that the variance of u given x is not equal to sigma squared in. Sigma squared in basically signifies the situation where the variance of each ui, that is u at each location I, is going to be sigma squared and off diagonal elements are zero. So there is no dependence in spatial error. When we relax this and we introduce spatial dependence in regression models, that is to say that variance or covariance of ui uj, where I and j can be seen as location markers, then this term will be not equal to 0, at least for some I not equal to j locations. So what we are doing is we are moving forward, or we are relaxing this assumption of spherical errors, and we are moving to a situation where the errors may be non-spherical in nature, also termed as heteroscedastic systems. And then we talk about, okay, what is the impact of having this non-classical situation or setting? And we have seen that this is going to be quite prevalent with spatial regression models. In fact, when we studied spatial statistics, spatial dependence, spatial clustering is one of the fundamental pattern with spatial data, right? So when we come to regression modeling, spatial dependence in errors is not surprising. In fact, it is a fundamental feature of the spatial data. With our example of price of homes, prices of homes are clustered together as well in their levels, in the sense that highly priced homes are likely to be located in regions where all other homes are also highly priced, right? And that's how we have these terms like posh communities, which basically means that in this community all homes are highly priced, right? So this phenomenon then turns out as this feature where mathematically we can say covariance of this unaccounted term in my regression model is exhibiting spatial dependence. We looked at inference properties, that is, what happens if this is a situation to my regression estimator, and we saw that the regression estimator will still be unbiased, but it will now be inefficient. We then introduced this FGLS estimator with the variogram model that we have looked at in the previous portion of this course, right? The second type of spatial dependence that we have seen is through Mansky's dependence reflection problem, right? Mansky's reflection problem applies to settings where, let's say, in a peer network, when I look at the performance of any student, it's not just a reflection of their own aptitude and their effort levels with regards to studying the course, but it also reflects the peer group in which the individual belonged, right? So in a way, an individual's performance is a reflection of the peer group's performance and vice versa. In such situations, we have seen that it's harder to argue causal inference. And then we studied methods for reconciliation of this reflection problem. And finally, we introduced this idea or this notion of spatial lags in regression models in order to generalize how to work with spatial dependence, in specifying spatial dependence either in the outcome mean or in the error term, in a more generalized settings like the irregular lattices, right? So you can go back to previous lectures and revise these concepts, right? So we've seen this earlier, but I'm just presenting this idea of spatially lagged variables in a regression model. I have this first thing called as a spatial lag or spatial autoregressive model, right? It is a model that comprises spatially lag dependent variables. An example here is written as W times G, something again we have seen in the past. What this is suggesting, W is called as the weights matrix. The weights matrix characterizes neighborhood properties. It generalizes this notion of spatial lags, right? And W times G is accounting for the the average behavior of what's happening in the neighborhood vis-a-vis this outcome variable G, right? So the spatial lag model looks like the following. We have an outcome variable G. In this case, we have seen examples for groundwater data. So let's say we are trying to model groundwater dynamics, and we have a column of data of groundwater levels at different locations, that is, let's say different wells, right? And this G is then modeled as a function of its lag, GL, which is the lag being it's the average, a weighted average of what's happening around to each, with regards to each location I. There is a parameter sitting in front of this GL parameter, this GL variable. So this parameter rho is a measure for the extent of correlation or dependence between the outcome variable and its neighborhood, averages. Plus our traditional x beta plus u, right? This lagged dependent variable, when included as a regressor or as an independent variable, we call this model as a spatial lag model. Note that GL is nothing but W times G, which is to say that there is a n by n weights matrix that characterizes neighborhood properties, something that we have seen in the previous lecture. I'll just revise it very quickly in a minute. And then G is a n by 1 matrix vector. So overall GL is nothing but a n by 1 vector, right? We will emphasize the need to check matrix and vector dimensions going forward when we work with these these models, because space by its own virtue brings in heavier notation, keeping track of neighbors. I has neighbors as J, K, and L. J may have neighbors as K, L, and M, but not I, and so on and so forth. So if you have those situations arising where some of my neighbors are not neighbors of my own other neighbors, then in order to generalize that notation, we use matrices, which are very convenient. But then when we actually do the math and we specify these things, we should keep a track of the dimension of these matrices, something we'll emphasize as we go forward. The second type of spatial regression model that we have seen is called as a spatial cross-regressive model, or the SLX model. In this case, I will be modeling G as a function of x beta, but also including Wx, which is nothing but the lagged version of x, right? So if I'm thinking about my example of, let's say, groundwater data, and one of the regressors is rainfall. Now, rainfall is very important in explaining groundwater levels. If it rains more, there'll be more regeneration, more sort of water entering the water groundwater reserve, and the groundwater level will come up, and hence my observation of groundwater levels will change. Now, you can imagine that when you look at groundwater level or groundwater recharge at any given location, it's not only going to be the rainfall at that very location. It's also going to account for the rainfall levels around or in neighborhood of that locations because of various geographic regions, right? It is possible that the location of interest by itself is in a low elevation, so rainfall that happens around might all run off to this location and hence feed into groundwater levels at this given location of interest. So in those cases, a weights matrix can be applied to these variables, and we can define a variable xl, which is nothing but the lag of the covariates, right? Okay, and then we can have a vector gamma and u. This is a SLX model. Okay, the final form here is called as the spatially lagged model, where what we say is that we have G equals rho, x beta plus u, such that u has, u exhibits spatial dependence. Again, we will, carefully one by one review these models, so there is nothing to worry about, but I just wanted to, provide a quick exposition of these, so that, in our coming discussions, these notations start to, become, you start to become more and more comfortable with these notations. Okay. All right. So just before we move forward, I just want to recall this idea of spatial weights matrices. So, the weights matrix is a device that characterizes neighborhood connections. So we have a abstract situation on the left, which has been adapted from Anselin's, lectures. So we have these 6 polygons, which some of them share borders, some of them don't share borders. And, we can focus on, let's say, polygon 6 and polygon 1. Right? The weights matrix on the right hand side is representing the neighborhood structure for these, for this given polygon structure. Right? So because I have 6, units, spatial units of interest, the size of this weights matrix is 6 by 6. Because the row represents each unit 1, 2, 3, 4, 5, and 6, and the columns are representations of neighbors, right? So columns also have representations of neighbors. Now, because 1 is not her own neighbor, so the diagonal element is 0, right? It's 0, 2 is not her own neighbor, 3 is not her own neighbor, 4 is not her own neighbor, 5 is not her own neighbor, and 6 is not her own neighbor. So all the diagonal elements are 0. The off-diagonal elements switch from 0 to 1 only when these spatial units share a common border, right? So that is the characterization of spatial linkage in the data, right? Now with 1, 2, 4, and 5 are neighbors, so we have a 1 sitting right, at column 2 row 1, column 4 row 1, and column 5 row 1. Note that we still have zeros in columns 3 and 6 with respect to row 1, because they do not share a border with unit 1, right? My second unit of focus is 6. So 6 is neighbors with 1, has only one neighbor, which is 3. So in the row that characterizes neighborhood structure for unit 6, I have zeros everywhere except for column 3. Okay, so I hope this makes things clearer. Something that we also discussed at length earlier was the row standardizations of these weights matrices, and we discussed why that is absolutely a critical idea. So I'm not going to go over it. You can go back and look at it. But the point that I'm trying to make here is that every time in going forward we see a W, I actually imply W tilde. That is, I am always implying the use of a row standardized weights matrix. We cannot use the raw weights matrix, and it's a good homework for you to understand this lecture. You can go back and review the previous lectures and see why is row standardization a very critical entity. Okay, so now we are going to start with what is called as the spatial lag model and look at its characteristics in detail. So let's write out the spatial lag model and go from there. So we have y equals rho wy plus x beta plus u. So we are including a spatial lag, and like I said, whenever and wherever I use this matrix W, I mean a row standardized version of it. So you can go back and check, but it's very important to understand that we are always using a row standardized weights matrix. So I have a column of data which is n by 1, Why is n by 1? Because I have data which has ID, location markers, you can have the coordinates, and then I have y, right? So I have, let's say, 10 data points, right? Then I have my xy coordinates for these 10 data points, right? And then I have values, let's say 10, 9, 7, 6, and let's say 10 again, right? So I have these n minus 1, n by 1, this n by 1 column which characterizes my dependent variable. That's what this y in this matrix form of this regression signifies. Okay, w times y, we know that if we have 10 entities, the size of w will be 10 by 10. So n by 1 entity, the size will be n by n. Y we know is n by 1, so these two combined will be a n by 1. X is a n by k, so there are k different covariates, and they have n data points for each covariate. And for each covariate, I have my parameter vector given as beta, right? And u is again n by 1. So I have a n by 1 on the left hand side and n by 1 entities on the right hand side, which is a must because I can't really sum two vectors of different dimensions. I can't be summing n by 1 with some m by 1 or l by 1, right? So I need exactly same dimension for each element that is linearly summed together. So it's a nice check for us as analysts when we are doing these things analytically. Okay, so here rho is called as the spatial auto regressive coefficient, right? Like I've said, this coefficient measures the extent of spillover effects that I has from its neighbors and vice versa, right? So I also exerts impact or spillovers on her neighbors, right? So the spillovers are both ways, right? We have talked about that in spatial data. It's not like time series, it's not unidirectional, it's multidirectional, right? And also we don't have a regular lattice to work with. We have irregular spacings of entities in space, and they are of different size and so on and so forth. So we have to account for those situations, right? So we can call this equation 1 and we can rewrite equation 1 as under. We can say y minus rho wy is equal to x beta plus u. Aha. So now we have, if we look at the left hand side as a consolidated regressor, right? Sorry, regressand or the dependent variable. Then on the right hand side, I have something that I'm very used to with regression analysis, right? So this is an important enough equation, so I'm going to call it equation 2. I can rewrite equation 2 as follows. I can say I minus rho w y equals x beta plus u. So this I is an identity matrix. Now the question is, what should be the size of I? Let's think about it now. So y is n by 1, x is n by k, beta is k by 1. So I have a n by 1, u is n by 1, right? So I need a n by 1 on the left hand side, right? W I know is a n by n. Rho is just a scalar. So it is just 1 by 1, right? So it is just a scalar entity. I, because W and I, we have a linear operator, which is a subtraction sign in between, I must have an identity matrix of size n. Identity matrix is a square matrix, n by n matrix where the diagonal elements are all ones and off diagonal elements are 0, right? So I minus rho W is some kind of a filter. It's kind of a filtering of the spatial impacts from the overall I, right? So I have this I minus rho W times Y. So I have a n by n sitting here. N by n times n by 1 is a n by 1. So kudos, right? So I have n by 1 again as each element in this equation I'm going to call it 2 prime. Okay, all right. So now this I minus, note this I minus rho W is known as a spatial filter, right? And I'm going to say this is similar to the detrending device or the detrending activity in case of either time series data, if you have seen time series data in the past, or even when you use panel data, you can detrend your data. Okay, so this is a spatial filter. As a next piece of activity, I'm going to pre-multiply 2 prime with I n minus rho W inverse. Okay, what does that give us? It gives me y, okay, it returns back my original dependent variable, equals I minus rho W inverse x beta plus I minus rho W inverse u. Okay, again, I will check dimensions, very, very important, check dimensions. Because we are working with heavy matrices, checking dimensions will provide us a nice, quick check on whether we should move forward or hold on a bit and make sure that we are, whether we should revisit these things. So I'm going to do that. I have an n by 1, I'm used to this. I minus rho W we saw here it's a n by n matrix. So its inverse, the inverse of an n by n matrix is also n by n. So I have n by n sitting here. I have n by k and k by 1 as x and beta. Again, I have a n by n and a n by 1 as u. So now I have this will give me n by 1, and n by n times n by 1 is again n by 1. So nice. And n by n times n by 1 will be n by 1. So we are done. So we have what we can work with. It looks like a legitimate, regression equation. So I started with model 1, and all I'm providing you are some algebraic manipulations of it. But as we move forward, these will come out to be crucial in terms of providing interpretation to these devices. Okay, so with that, we are going to move to a question that is usually the question that applied econometricians ask, or applied social scientists ask in general, or applied sciences, scientists are also interested in, is that what is the change in y as a result of a small or marginal change in x? So if I were to shock this regressor or covariate matrix x by a little bit, let's say I move from a lower rainfall to a higher rainfall world, lower population to a higher population world, a little bit, what is the impact? So of course, when I'm changing x, I can change any one covariate. So I'm talking about these things in the spirit of all else held constant. Okay, so my query in mathematical language, so I've written an English language term. Now I'm going to write down the corresponding mathematical language term, is basically saying what is the expectation of y given a small change in x. So I change x and I want to know as a result what is the average y. Okay, so this will be equal to, because all else is held constant, so u will be kept as constant. So as x shocks, as I get a shock in x, I don't see any shock in u. So I have I minus, right? By the way, I'm looking for change in y conditional on change in x. So I have I minus rho W. I is of size n because we have seen, times delta x into beta. Okay, remember beta is a parameter which given data we can estimate from the model, right? So you can imagine that let's say you have beta and then you're trying to evaluate some policy or some shock in this variable x. Okay, now we have this, you know, I minus rho w with an exponent of -1. So this can be then further expanded using the power series expansion of a inverse function, right? And for that I have a specific resource for you to read, where I'm going to request you to read inverse series expansion and more generally Taylor series expansion. If you have heard of this mathematical concept of Taylor series expansion, we are basically going to apply that. But as a special case, you can read power series expansion and try and understand where we are coming from, right? So I'm going to just say here, apply power series expansion to I minus rho w inverse. Okay, so I minus rho w inverse can be then written as I plus rho w plus rho square w square, rho cube w cube, keep going as an infinite series. Okay, and then obviously, I'm going to just put a marker here. Just a sec. Very, very important. Read Taylor series expansion. So, okay, so I'm going to just name this new important equation, that is the change equation in expectation, as equation 3. And then with this idea of Taylor series expansion, I'm going to take it, assume it that you guys are going to go back and read what Taylor series expansion is. If you're a student of economics, it's really important. In fact, Taylor series expansion is what links the comparative statics of the, let's say the utility maximization model or the expenditure minimization model, profit maximization model, the comparative statics of these models or these algorithms, the linkage between them and our regression models and our exercising or mobilizing the causal inference idea is via the Taylor series expansion. So that's a matter for separate discussion. But what I'm trying to motivate you to do is to definitely read and study Taylor series expansion at your time. Okay, it's very important. Okay, so then 3 will become the following. So expectation of change in y conditional on a small change in x can be written as I plus rho w plus rho square w squared plus rho cube w cube plus keep going times delta x beta. Okay, I mean you can set delta x equals 1 if you want, and you will see that how my model parameter beta will then explain the total change. Right now I can rewrite this as equal to delta x beta, because once I multiply I with anything, right, any matrix multiplied by identity matrix is the matrix itself, plus all of this remaining term of rho w plus rho square w squared, rho cube w cube, keep going till times delta x beta. Now, this is a very tractable, intuitive entity. Why? Because delta x beta is something that we are used to. If rho was equal to 0, if there was no spatial impact, there was no spatial lag term, right? Then all we are left is delta x times beta. This is something that we are very much used to, while conducting, understanding the change in y due to change in x. So, in case of spatial regression analysis, we will interpret delta x beta as the impact of a marginal change in x, at the location of this change or shock, right? So at the location of change, this is how much impact I will have. If there were no spatial impacts, there were no spatial spillovers by virtue of this model parameter rho, then all I have is delta x beta. I'm very much used to it. This is further defined as what we call as the direct effects, the direct effect of change in x. The second effect you can imagine is called as the indirect effect, and that is this remaining term which says the impact of marginal change in x on first order neighbors. Okay, second order neighbors. Okay, third order neighbors, and so on. And this I am interpreting as an indirect effect. Now, I've written these first order neighbors, second order neighbors, and third order neighbors in different colors. Why? Because if you pay attention to what you are looking at, rho times W characterizes linkage with neighbors. Okay. Now, this rho W is a marker for first order neighbors. Okay, this is the first order spatial spillover. Rho square W square has this term W square. What is W square? W times W, right? So now a square matrix multiplied by itself is going to express. You can work it out, at your own time, but this expresses a second order spillover effect. So if I have an impact at location I, rho W explains an impact on locations which are immediate neighbors of I. But by virtue of change at locations which are immediate neighbors of I, will have also an impact on the neighbors of those first order neighbors of I. That is captured by this rho square W square. Okay, so this is the second order impact. And then we have this third order impact. Okay, so we can then interpret expectation delta y given delta x as, we'll rewrite rho I plus rho W cube delta x beta. This entire entity is called as the spatial multiplier effect. So it's a device which is able to measure the spatial multiplicity. We'll look at some of the properties through some, we'll just formalize these things through some notes. Okay, so the first note that I want to make here is that whenever rho is less than 1, in fact, it can be positive or negative. We are usually working with positive spatial spillovers. That's the idea of spatial contiguity. So we're usually working with a positive rho. But when rho is less than 1, the spatial multiplier effect declines exponentially with distance. Right? What does that mean? So if I go back to my formulation, let's say if I were to draw a graph where I have distance on, or some kind of a lag measure on the x-axis, and I have the impact measure on the y-axis, then the origin on the x-axis will mean own location where the shock has happened. I will then have first order neighbors. Okay, farther than them will be second order neighbors. Farther than them will be third order neighbors. And I can keep going like this on the x-axis. Okay. What's the impact at own location? The direct impact measure, which is delta x beta. What about at the next first order location? Well, it's going to be slightly lower. It's rho times delta x beta. So, it's going to be rho w delta x beta, right? At second order neighbors, I'm going to have rho squared w squared delta x beta, right? And then so on and so forth, right? So I'll have a impact here, then an impact here, a impact here, here, and so on and so forth. So what, by virtue of specification of my model, because I have spatial dependence through this rho parameter, through the specification of this, because of the way we specify the spatial lag model, the spatial multiplier effect takes an exponential shape in terms of the decline of the effect through distance, which is intuitive, right? I mean, if you're going to have a shock in terms of spatial spillover, of course, the spatial spillovers are going to, spillovers by themselves are going to become weaker and weaker and weaker as we go away from the entity of impact, right? Okay. So that's the first pointer. The second note or the second pointer is that in presence of a spatial lag, that is rho, right? Oh, sorry, no, it's not rho, it's wy, right? We have total effect of change in x, that is delta x, is greater than delta x beta, right? So if you ignore spatial dependence, right, you're going to account all of this. You're going to inadvertently, either this will all come to the direct effect, so it will be a biased effect because it will also account for what's coming as a spillover, right? And further, it might actually enter, as a confounder and hence articulate the bias, right? So they are the same things, but the idea is that you will be misinterpreting the effects, as totals will not come out to be exactly as delta x beta, right? Okay. All right. Something that we have seen, note 3, I'm just going to say notes. Okay. Sorry about that. Okay, different topic. Let's go previous. Okay, let's add a page. Okay, so notes continued. Okay, the third note is on the direct and indirect effects of a spatial lag model or in a spatial lag model, right? So you have seen these things earlier. So direct effect due to change in x, I'm just going to say delta x is just delta x beta, and the indirect effects due to delta x is given as rho w plus rho square w square plus rho cube w cube plus keep going times delta x beta, right? We have seen this. This can be written as I minus rho w inverse minus I times delta x beta. So just, simple algebraic manipulations are able to provide us these understandings. What is interesting maybe is the visualization. Let's visualize these effects. So let's say I'm talking about an entity I, right? The entity I can have the following neighbors, right? All these entities could be, let's say, J1, J2, J3, J4. Entities J can themselves have their own neighbors, right? So j's can have their own neighbors, and we can then term them as k1, k2, k3, k4, k5, k6, k7, right? These entities can then further have their own neighbors. So, of course, in space, every entity will have neighbors. The direct effect is the change that happens delta x beta due to shock at location I, right? What spills over to its immediate neighbors is given by this W times rho, multiple. This is a first order effect. The second order effect is characterized, then second order indirect effect is characterized as rho squared W squared delta x beta, right? So these mathematical entities have very interesting, characterizations, so as to say, spatially. Now, as an application for policy, what this really means is that the spatial lag model is able to measure the effect of change in a policy variable x at a certain location I that extends beyond I, right? So a policy shock on location I can have an effect beyond I to its first order neighbors, to its neighbors, or neighbors of neighbors, or neighbors of neighbors of neighbors. So which order neighbors, that's not the point. The point is a shock at location I can have impact on locations beyond I, right? In other words, the spatial lag model will allow us or help us to simulate the spatial imprint of a policy change. So I'm going to write it down that a spatial lag model helps us simulate the spatial imprint of a policy change. Okay, should think about it a little bit. Okay, all right. So the last topic in spatial lag models is the impact of misspecification of OLS estimate on inference. So we have written down this model. We say y equals rho wy plus x beta plus u. Here this wy is nothing but y lag. Of course, the vector notation is used differently between what I am saying and what expressed on your screen. So, I'm just going to say that y under bar is the same thing as y vector. All I'm trying to say is we have a column of data. Okay. All right. So the question is, what if I were to ignore this spatial regression, spatial lag term, when it indeed should have been in there by virtue of the population process? Well, if it is ignored, it's going to go and sit in the unobservable term as if, I didn't observe it because I've ignored it. So what's the implication? So, Luke Anselin provides a very nice depiction of, what happens if you ignore these things through a simulation. So what you see on your screen is a scenario where this parameter rho varies from 0 to 0.9. I have said earlier, if rho equals 0, the total effect is just delta x beta. But if rho is not equal to 0, total effect is greater than delta x beta, right? So this density function in blue or in purple characterizes the expected value of beta hat when rho is 0. This is the precise effect parameter when there is no spatial autocorrelation data. So if there is no spatial autocorrelation data and we ignore it, we are fine. But let's go back and look at an extreme case where, let's say, rho was equal to 0.9, which is this, brown looking or, red looking curve. Here, the expectation when we do include beta hat comes out to be much larger than the case when we did not include, when rho was equal to 0. Why? Because the total effect is now also accounting for the spillover effects, something that can be a spatial spillover. So, theoretically, we saw total effect is greater than delta x beta, when you have a higher, when you have a spatial spillover through the spatial lag, term. This graph tells me if I were to ignore, if I had rho equals 0.9, but I altogether ignored this term rho x, rho wy in my regression model, I will still end up with the blue curve, right? So I will still be this, representation provided by expectation of beta hat when rho was equal to 0, right? The distance between these two articulates the bias. So what happens if I ignore spatial lags, and they should have been included, is that I will have a bias in my beta hat, estimator, right? So the OLS estimator, the bias is more and more severe as rho goes up, right? Another thing to look at is that bias is not, direction of bias is not, it is not just that it will be underreported, it may even be overreported. And we go from rho equals 0 to rho equals 0.2, the total effect actually comes down, right? So it doesn't just provide me a direction automatically. So these things are they depend on context, they depend on the setting, and so on and so forth. The point here that I'm trying to drive home is that we cannot really avoid or these effects when they are indeed present in the population process. If we do, then we have a sort of a misrepresentation of the population that we are trying to you provide an explanation for, and so on and so forth. Okay, so that's it for the spatial lag model. As a next step, we are going to look at the spatial error model in detail. Okay, thank you for your attention.